probably tell by my accent I am French. No, I'm here from Boston in the US. I do have to say that the 30 degrees in Boston means that it's really cold and snowy, and apparently 30 degrees here means that it's really hot and muggy, so I'm not sure which is worse for me. I do want to talk about end-to-end or bust is the title. I didn't come up with that. I probably would have been a little more humorous. Really, I want to talk about getting data between the cloud and the edge and how to do this safely and securely. And I'll talk about some of the lessons that we have learned at Resin as I do so. So my not a pitch disclaimer actually comes in the form of an apology. I'm a terrible artist, so what I did was I cribbed some of the slides that we had. So you may see a couple of logos and things, but I promise I will not use those logos to sell you anything. I won't talk about them. We'll just use them for the diagrams that they have in them. I'm also going to cheat a little bit because the topic here is end-to-end or bust, but I'm going to get there in the end. But what I'm going to do is sort of rehash and recap some of the things that have gone on through this past couple of days, talking about particularly how the Internet of Things really sucks, but hopefully shed some rays of sunlight on that and talk about how we can fix those things and actually actionable ways, things that we can do to make this better. And so I said I would recap things, and I'm going to start by the very simplest one. Everybody is probably familiar with this if you've ever even looked into the Internet of Things, right? This is basically how you build an Internet of Things project. You get a bunch of devices, you put them out in the world somewhere, you deploy your software onto them, you put them out in the world, you connect those things up to some cloud service, and basically at this point you're done. Right? You've got devices out in the field, you've got something on the back end to deal with this data, you've got connectivity between them. So at this point, our three-step process is really finished. Now, anybody who has actually used an Internet of Things project or built one knows that there's at least one more step here. And that step is everything goes horribly wrong. As soon as you put things out in the real world, as soon as you are dealing with devices that are not under your direct control and are not something that you can just reach out and touch and reboot or fix when they break, this is going to happen. This always happens, and I have been burned by this many times. All of the sort of IoT House of Horrors things have all happened to me, so I have very personal experience with this. Now, there's another step that comes in this kind of life cycle of an IoT project, if you're very lucky, and that is somebody comes and fixes the thing. So if you have a responsible company who made this device that you've put in your home and then has caught on fire, they will fix the thing, ideally. But the problem is, often they're not going to do that. And the reason is that this is a really expensive and difficult process, right? We all know that once those devices are out of our control, once the company has pushed those out to wherever they are, you often are going to have to send somebody physically to touch those things to do these updates. And anytime you get people involved, as we've heard in the past few talks, this becomes really expensive. So it's kind of natural that the attitude that many companies have is, if it breaks, you get to keep both pieces. Not my problem anymore, you bought it. And I think a lot of this is, I mean, maybe some of it can be attributed to malice, but I don't think all of it can. I think a lot of it really boils down to not having the tooling and infrastructure to do this, and not having thought about this from the get-go. Really, again, when I started this project, I really just thought I need some devices, I need connectivity, and I need something on the back end to pull all this data in and deal with it. And I didn't think about what happens when things go wrong, because nothing ever goes wrong in my QA lab. I fixed it when it did. So one thing that may be in people's minds at this point is, well, do you really need to think about how these devices are updated? Because they do, in fact, have this connectivity. I do have a pipeline from the cloud to the edge at this point, right? There was something feeding data into my cloud service. Therefore, I can just use that same connection to push data back. Well, the problem there becomes that's really your only pipeline. And if you do a bad push, now you're stuck. So again, we've gone from maybe being able to do something, and I've pushed that bad push, pushed my head through the chair here, but now I'm stuck, and again, I have to have a lot of people involved. So you can see we've got people with hacksaws, and we've got people holding the chair. It really becomes a mess to deal with this sort of thing. And we know this firsthand. This is not a pitch, but this is the experience that we've had at Resin. The basis of this is because there was a project, if anybody remembers all the way back to 2012, the Olympics were here in London, and some of the folks that went on to found Resin, were responsible for creating a digital signage platform. So the idea was you would have these rubbish bins and you would have walls and all these surfaces would have remotely updatable signs. So signage, advertising, that sort of thing. It's a really simple problem. You get a cloud service, you get connectivity, and you get some devices, and you're done. Which is how we had people with PhDs in computer science walking around in the winter in London with USB sticks and USB keyboards trying to fix these devices when there was a bad push. Once there was that bad push, we were stuck. So I'm going to shift a little bit and talk about how this functions, how devices can function better. And I love this quote. This is an O'Reilly quote. "The web brought about the end of the annual software release cycle." Now, if you think about this, if you remember what software used to be like, maybe the late 80s, early 90s, you would go out, you would go to a store, you would buy a box from the shelf, you would bring it home, you'd stick the disks in your computer and install the thing, and that was pretty much it, right? Once you had bought it, it was yours, and if something didn't work, if you were lucky, maybe somebody would send you a fix. But maybe they wouldn't. They probably just wouldn't care. And if they did send you a fix, it would take them a long time to get around to doing it. Sounds pretty familiar, right? That's pretty much where we are in the Internet of Things today. So we have to fix that. How do we get from where software used to be 20, 25 years ago to where software is today? Think about how software works today. If you have a security vulnerability in your product that's on the web, and you say, well, you know what? We'll fix that maybe 6 months from now. When we get around to our annual release cycle, we're going to fix your problem. You're going to be out of business really, really quickly. So this is why we say those who ship code will succeed. When you have the ability to push things out into the world, out to the edge, whatever that edge happens to be, very, very quickly, if you don't take advantage of that ability, then you are going to be eclipsed by people who do. So you're either going to have such bad press around your terrible security flaws that you're not fixing that people are going to stop buying your products, or worse yet, one of your competitors is going to come along. They're going to build a very similar product, but theirs is going to work better because they're adding features, they're updating their security, they're pushing these updates out into the world. But how do they do that? How do we do that in a software context, and why can't we do it in a device context? I think it really comes down to tools. And this is the ray of sunshine part. This is where I say I think we can make things better. If you think about what a web developer is doing today, when they're developing software, it's a very simple process to go through and create new code, check that code in, have it tested, have it run through an entire gauntlet of integration, and then finally deployed into production. So you think about this isn't an annual process. This is the process that had to be developed to deploy code very, very quickly. And the last time I checked, I think Facebook is deploying code to production, facebook.com, twice a day. So this is a cycle that is happening non-stop. This is a really rapid fire process. So in order to support that level of speed, you had to build really fantastic tooling. So we've got our happy little developer here who is writing code, but on the back end, there's a whole bunch of automated systems that are taking care of a lot of the drudgery, a lot of the testing, and a lot of the things that need to happen for that rapid fire deployment process to work. So what if we could take this same process and apply it to the Internet of Things? Not changing anything, not adding new tools, but just adapting the existing tools that we have to IoT. So I'll back up a little bit right now and say, why do we need to do this? Well, it's very obvious right now that scale is a concern, right? There are more Internet of Things devices going online now than there are mobile devices. And there were more mobile devices than there were PCs just a few years ago. So the orders of magnitude of number of devices that we are dealing with are increasing year over year. So it's a massive kind of hockey stick problem. But at the same time, these devices are getting more complex, and several people have mentioned this throughout the sessions today. These devices are getting more complex in a couple of different ways. And what I mean by that is complexity is, on the one hand, the ability of the device to do work directly. So the complexity of the device insofar as it's just got more moving pieces. If you look at that Raspberry Pi that we all just got today, it's got, I think the model that we have has a gig of RAM and a quad-core 1.2 gigahertz processor. That machine, that little thing that comes in a cardboard box that you can go out and buy for 30 pounds is way more powerful than the machine I took to university to get a computer science degree 20 years ago. So these devices have gotten way more complex in the sorts of problems that they are able to tackle. And because of that, we are asking them to tackle more complex problems. So along with all of that added capability comes additional layers of software. Right? We've got a full OS on this device. It's not an 8-bit microcontroller. It's not something that's just sitting here throwing out temperature data. This is basically a server that has been put on the internet somewhere and needs to be treated just like a server. But the real problem is that we just don't have the number of developers in the embedded world to deal with this. This is really what I think the core of why the Internet of Things sucks so bad today. It's not because people really intentionally want to leave these devices unsecured out in the field. It's because there just aren't enough developers to keep up with the number of devices and the continual growth in complexity and scale that we're seeing. So we have, 9 million mobile developers right now, 8 million web developers, and 600,000 embedded developers. There are just not enough developers out there to pick up the slack if we continue relying on embedded tools, the traditional embedded tool chains. And there's more to it than just doing kind of security updates, right? This is really the promise of edge computing, promise of the Internet of Things, is that we really want to be able to push as much of that processing and as much of that computation out to the edge as possible. You think about it, if you're deploying sensors out in the environment, it's because you want to gather information, right? If you already knew what was out there before you deployed those sensors, there would be no point in you putting those sensors out there in the first place. It just makes sense. But once you have gathered that data, you now have a better idea of what the environment you've placed those sensors into looks like. So what you really need to be doing is continuously evolving how you are working with those sensors out in the field. As you have put those sensors out there and gathered data, you've pushed it back up to your cloud service, you now have a better model that you've generated of what the environment looks like. Well, wouldn't it be great to take that better model and push it out to the edge devices so that you're not sending as much data, or they're doing more of that processing out in the edge and offloading it from your cloud services? That's really what the promise of edge computing is, and this is where we need to get to. So I do want to talk about one of the tools that is in that web developer's tool chain that he's able to use to push code and manage code so quickly and easily, and that is Docker. And this is containers in the other sense. So these are not containers that are sitting in a shipyard somewhere. These are containers, these are Linux containers. And if anyone's not familiar with Docker or containerization, it's really very simple. The idea here is that a container just has it's like a virtual machine without the virtual part. It has your file system, it has all your libraries, it has your application. It's everything you need in order to run your application in production. This is, incidentally, a server-side technology. This is what Docker was built for. Docker was built so that if I have a huge amount of resources, I'm in AWS and I've got thousands and thousands of servers, and I want to be able to do things like scale my web server out, I don't want to have to redeploy new instances of the web server and do a bunch of configuration and so forth all the time. I just want to say, hey, I've already set this thing up, just go push it onto a server, and I don't even care where. So people who use Docker tend to talk about things like cattle and pets. We don't treat our servers like pets. We don't give them names. We don't care about them. If one of them gets sick, we're just going to take it out back and shoot it in the head and replace it with an identical copy. But that's absolutely not the case in the embedded device world, right? If I've got an embedded device that's sitting in a power generating station, a power generating turbine that's on top of a mountain or out in the middle of the ocean, if the telemetry system for that thing or the control system for that thing gets sick, I absolutely want to get it better because it's going to cost me tons and tons of money to send somebody out there and physically touch it. So, having said all this stuff about just taking things out back and shooting them in the head, why does it make sense to do this using Docker in an embedded environment? Well, you did hear a little bit of the demo that we did. We did demonstrate using Docker to update a drone flying on stage. And unfortunately, I am not a drone pilot, so I can't show you guys that. But there's a video of this if you Google for DockerCon 2016. That's where we showed this. But the whole idea here is that we used container technology to be able to update this drone in flight without physically crashing the drone. Without actually, if there were an issue there, we would have crashed the thing and we'd have been out many thousands of dollars. So how does that work? How do you use Docker containers in an embedded device? Well, I've got a device and I've got a container on it. And this container, like I said, this has a file system, it's got all my libraries, it's got my application, it's got everything I need to run my device. but there's an issue with it. You can see this container is kind of old and busted. I need to fix that. Well, because everything is containerized, I'll cheat a bit and say, we can't treat things exactly like cattle, but we can do some of the neat duplication stuff. So I can push a new container onto this device, and this container can have my updated code. So this has my bug fixes, my security fixes, whatever I want to put on that device. And I can run these two containers in parallel and gradually transfer over all of the resources that are used by the original container into the new container. So my gyroscope on my drone, or the camera controls, or the network controls, everything, every sensor that is on that drone, every bit of flight control software can be gracefully handed over from the running application to the new version of that application. And once it's done, I can just shut down the old container. So at no point do I ever have to reboot the device, at no point do I ever have to do anything truly disruptive. So this is a way of being able to manage code on devices without having to really worry about firmware updates going bad. Because if I go back here and if my new container ended up being bad and this handover step didn't happen, well, I'm not really any worse off than I was before. I'm not bricking anything. All of this is in a container, so I'll just, I'll take that blue container out and maybe I'll push a yellow container onto it. So it's a really fantastic way of being able to work with the resources, even on a constrained device, without having to worry about losing access to those resources. And this is where a couple of the logos sneak in, so don't look at the logos. I just want to talk about what that architecture looks like on a device. Really what we have is that you have a thin layer on the device itself, so the absolute minimum OS that you can get away with, and the engine for Docker to run. Everything else happens inside of a container in this model. So the idea is I push my application's inside of a container, and I have perfect control over the state of that application. The really cool thing here is that I can start applying this model to the control systems themselves. So everything that I'm using to do those updates can also be part of a container and can hand over very gracefully. So I've finally winded my way around to the actual point of the talk, which is devices that are on the edge. So everything I've been talking about is more complex than an embedded sensor or an embedded device. So how do I manage an embedded device and still have this level of safety and be able to update things in the field and not leave people without their devices, without access to devices? We can use that same model, and we've got some ARTIK logos on here as well, so Dan will wave, and you can ask him about the ARTIK side of things. Basically, we can use the exact same model, but we add one layer of indirection in there. So you've got a device that you're still managing with these Docker containers, so something fairly heavyweight and complex. But that particular device then goes on to manage all of the devices that are not capable of running Docker. So all of the things that do just have 8-bit microcontrollers and have firmware. So again, we're pushing the control of this and the responsibility for this out to the edge. So the device that's sitting on the site with the sensors and with the embedded devices is the one that's responsible for keeping track of those devices and making sure that they get updated properly. So again, it's not something that we have to worry about remotely, and if there are bad pushes or bad updates, it's only happening at the edge, so we can always go back and redo those. So these are the sort of, won't get to that yet. These are the sort of technologies that I think if we take them from the web world and adapt them to the IoT world, we can see a massive increase in reliability, in maintainability, in updatability. These are the sorts of things that we really need to be thinking about. How do we adapt these existing tools and bring them to the IoT world? And so, having finished that part of the talk, I wanted to mention one cool thing because I didn't get to bring this with me or do a cool demo, but this is also online. One of the cool things that we've done at Resin recently is we built a Raspberry Pi cluster of 150 devices, all controlled using exactly the model that I just talked about. So we can, we can push code to them remotely, we can view them. But I was looking at pictures of this and I kept kind of feeling frightened by it, and it wasn't until that I came to London that I realized why I kept feeling the urge to dive behind a sofa every time I looked at it. The thing really reminds me of a Dalek. So that's it. Thank you very much.